So big questions that machine learning methods can answer are this first one, is this observation, does it belong to a class A, B, or C, or D, or E, or something else? That's classification. We're classifying some new observation to see if it's a hamburger or a hot dog, or a blueberry muffin, or a chihuahua, or a churning customer versus a non-churning customer. And we can have multiple outcomes. This isn't just binary, right? So we have a categorical target variable in classification. Categorical target variable in classification. And that's a pretty basic kind of question. Is this A or B or C? What class can we classify this as? Other big questions. How many or how much of something can we predict based on non-temporal data? Any data that's non-time, that's a regression. What groupings or what relationships exist in the data already? Folks, that's clustering. I want you to write all of these down, handwritten in your notes, or type them. If you got a pen, write them down. These 5 questions are a big deal. If you can wrap up and summarize your knowledge of machine learning with these 5 questions, whoever's listening to you is going to think, wow, that person really knows their machine learning. They didn't use any jargon. What groupings exist in the data already? That's clustering. Time series analysis is what's going to happen next or what's likely to happen next. And then anomaly detection, it's not just one algorithm, but really the question is this weird? Is this weird? And I struggle to find a single ML algorithm that doesn't fall into one of these buckets. And shameless stealing, because genius steals, I stole these questions straight from Microsoft on an intro to machine learning course. And I've been wanting to disprove them ever since, and I can't. So anyway, that's a big deal, these big 5 questions. So let's talk about classification. Classification is a supervised learning task. That doesn't mean there's a manager overlooking your shoulder. That means that you have labeled data, and your labels are the target variable that you already have. You already have the answers for supervised learning. You already have the answers for the data that you have. You don't have answers on data you haven't seen yet. So this is a perfect example, like the churn, right? We know what happened on the data set, and we want to build a predictive tool that can make predictions on new pieces of data, presumably that are similar to the training data. So we're only training on data with answers or labels. And the big deal, regardless of the specific algorithm, all of our classification algorithms are trying to help us produce something called a decision rule. The decision rule could be mathematically complex. It could be a curve. Your decision rule could be as simple as a straight line splitting 2 classes. Right? If you have a bunch of X's and O's and you have the labels for X's and O's, you draw a straight line between them if they're separable. The big deal with supervised machine learning in relation to classical software, well, classical software takes in rules that could be business rules, rules that could be tax law, that could be other kinds of law, regulatory law, rules of a video game, chess, whatever, and then data. So classical program example, TurboTax, you're calculating your tax liability or your refund. The rules coming in to that program are tax law. The data coming in is your data as opposed to my data, right? And then that application gives you some answer. You're going to get back an estimation of your refund or your liability. Now, machine learning so supervised machine learning, once we have answers on our training data, we change this up a bit. We provide raw data with the answers for the data that we have. And all that our ML is trying to do is approximate a function that's the decision rule in this case, or the trend if we're looking at regression, right? This is a game changer. With some of our first machine learning was autocomplete or spell check or spam detection. And lately we're seeing really, really impressive gains with ML. Get this tattooed if you're into tattoos, it's worth it. Maybe in your lifetime, there will be some other paradigm that expands our minds considerably. Maybe it's quantum computing. Maybe it's something else that we don't know about yet. But that's a big deal, because now we're able to take the power of machine learning and run it with computers, not just on blackboards and with theory, right? So let's talk about our main ideas. With classification, we are using labeled data to train our algorithms to classify new data points that were not in our training set. The training data allows us to train an algorithm to produce a decision rule. I'm going to give you a graphic of a decision rule momentarily. Here's the magic of that decision rule. You can use that decision rule as a boundary or as a way of measuring distance between points. We'll classify our points into the different classes. Here's our visual. Okay, we have an X that's color, and our color appears to be a gradient from red to very, very light orange. And our size goes from low to high. Now, what's interesting here, all of the apples and oranges, they have similar sizes. There's not like a heavy distribution of small apples and large oranges, right? So here's how to read this one. If we know the red and orange X's, those are labeled pieces of data in our training data set. The green line is the line of best fit that creates a decision rule. Notice how that's making a boundary. So if we get a brand new data point that was not part of our training set, and it's way over here, it's middle of the road on size, and it's extremely far right on the color, it's most likely an orange. Why? Because it's more similar to the other oranges based on color. This decision boundary is not going to be perfect. Perfection is for math class, right? And proofs. But in this case, we have misclassifications. We might have an apple that's classified as an orange, or an orange classified as an apple. This decision boundary isn't just somebody writing with markers through the chart. That decision boundary is produced mathematically from your model. Could be a straight line, could be a curved line in 2 space, could be a curved line in 3, 4, 5 space, right? It's tough to visualize that stuff. But all we're trying to do is use the labels to train our algorithm, so our algorithm learns what's the difference. And in this case, the difference is the difference in color. How is the algorithm able to do that? With labeled data. If you didn't have labeled data, we'd have to do something else entirely. You couldn't do classification without labels. Questions on this diagram, on decision boundaries, on supervised learning? I know we've been doing a deep dive into like stats and Python and storytelling. It's been a minute since y'all heard some of these terms. Okie dokie. Let's keep going. We can have 2-class classification, like apples and orange, cat or dog, and we can have multi-class classification. We could classify based on, I don't know, interaction with the curriculum, if somebody's a web dev student or a data science student or a cloud student, right? Our number of output categories is only limited by the data that's represented in our labels, okay? There's some vocabulary. I want to make sure this on a note card. I realize, yeah, even if we do a quiz on this, it's open book, open note, but I really want you to get your head around this stuff. A classifier is a specific algorithm that maps the input data to the specified category. Our classifiers could be any number of classification algorithms, but like if you said, hey, I did classification on this, I will ask, oh, what classifier did you use, or what model did you use? The classification model itself is an algorithm. Algorithms are series of steps, like a recipe, except very, very formal. That takes in patterns of input variables, generalizes those patterns, and applies them to new data to predict the class. The word feature is very, very specific. We've used the term column, independent variable, feature. Feature specifically is, it's a column that you are using to train your model on. If your model does not train on a specific column, that column's not a feature. It's just a piece of the original data. Binary classification is a 2-outcome classification, checking for the presence of something, churn, not churn, cat, dog. Multi-class classification is rock, paper, lizard, Spock, any kind of possible outcome. There's a big honking list of classification algorithms. We're not going to have the time to get into all of them, but I'm going to tell you something really awesome and special about sklearn. sklearn is the library. In fact, it's the world's leading library for Python machine learning. sklearn, once you learn 1 or 2 algorithms and how to call them and how to use them, I promise you, the modeling here is going to be the easiest code you do in the entire course. The hardest code is getting the data where you need it to be, or transforming the data into where you need it to be. But all of these models, logistic regression, decision tree, naive Bayes, k-nearest neighbors, random forest, support vector machine, gradient boosting, stochastic gradient descent, all these great tools all have basically the same way you interface with them. So we're going to cover logistic regression. We're going to cover k-nearest neighbors. We're going to cover random forests and decision trees. And you guessed it, random forests are made out of randomness and decision trees. Once you get your head around all 4 of those, or even just one of them, you can use any one of these other classifiers from sklearn, because the code doesn't change all that much. Maybe the hyperparameters, the arguments into the model function. I'm not going to oversell it. You'll see what I mean. Once you learn one, you can grab another pretty easy. Here's the thing though, we have to prepare our data, right? If you've ever tried to graph something where you had nulls and your graph blew up, or you've ever tried to do math on a column and you got back not a number, well, you can expect that your ML algorithms are going to blow up if your data has nulls or the wrong data types, right? Like if you have numbers that are in strings. So some additional preparation that we need to do. We'll talk about this in the preparation section. Our features, if our features are not already numeric, we need to turn them into numbers. Because all of our algorithms only eat numbers. Now that becomes very interesting when we have categories of things, right? We can represent a binary pretty easy, 1 or 2, or 0 or 1 rather. But if we have multiple options, we'll talk about the tools that we use to turn strings into numbers. Our categorical features or discrete features will need to be numbers that represent those categories. So even a categorical feature like traffic light color, red, green, blue, or red, yellow, green, we need to convert that into numbers, okay? Any continuous features, so any numbers, we might need to scale them. Now, scaling and turning categorical features into strings, that's a bit much to throw at you at once. So I'm going to tell you right now, we're going to, in the classification, we're going to put off the scaling of numeric columns until regression. Okay, and we'll talk about scaling a little bit later. The big deal with scaling is we don't want, if we have one column in millions of dollars and another column in centimeters, millions of dollars to centimeters, they don't have anything in common. Okay, so we'll talk about that more deeply. What we will cover in classification is what's called encoding. And that's where we take our categorical or discrete values and turn them into numbers. Okay. I've got a nice little, hey, look, it's a decision tree. Does your ML model rely on distance? This tells you if you need to scale the features. So if your model doesn't use distance, you don't need to scale anything. Right? How to tell if a model uses distance? Well, there's an argument called distance, because there's different ways of measuring distance. Okay, the preparation is critical. We can't just jam into a model with data with holes in it or dirty data. Okay, cool. I'm going to open up for Any questions so far on what we're covering? Conceptual questions. Yeah. Bert, what's on your mind? Let's talk.
So just to get this kind of straight, usually, so when we convert everything, and I'm pretty sure we're gonna go over this later on in the future, but when we convert everything to numbers, we're definitely gonna have to be writing a lot of that stuff down, right? Because when we do make, for instance, like a legend, we'll be able to, yeah.
Yeah, that's why we've got notebooks, so we can type text right next to the code, or comments if you're just in the code itself. Yeah, absolutely. Yeah, good question, Bert. Let's see, the next bit of the overview gets into some specifics on how some of these models work. What I want to do is go on a little side quest and visit about this decision boundary real quick, a little more deeply with y'all. Will that work for y'all? Getting some more visuals? Okay, let's do it. sklearn. So sklearn is the library that we're going to be using. If you go through the course without looking at the sklearn documentation, you're doing it wrong, right? Always look at the documentation. Always look at the documentation, right? Now, what's really cool about the documentation for sklearn is that it's very, very visual, and you have code that you can run alongside of it. So let's see, what does sklearn offer? Classification, which we're going to do, regression, clustering, data pre-processing. We're going to be doing more of that. That's the encoding, model selection. So how can we, in an automated way, select which model to use? That's kind of cool. Dimensionality reduction. Let's focus on classification first. So clicking on classification, we've got all these different types of models for classifying things. And let me see if I can't find, maybe it's in the user guide. Supervised learning. Linear models, no. Perfect. sklearn, what do I want to do? I want to find a spot that gives me a list of examples. Okay, perfect. We're talking about, so you don't get lost, we're talking about decision boundaries, right? And if our input data, let's take a look at our input data here. This is great. I'm going to share this with everybody. If somebody could paste this in Slack, I don't have Slack open, that would be great. With our classifiers, we have labeled data. So in this example, we have red data points and blue data points, and some of them are kind of on top of each other, aren't they? At least in this space. Now, what we're looking at is a table of different pictures. The nearest neighbors is kind of distance-based. So I'll give you the preview of nearest neighbors. If your data point is close to a bunch of red data points, it's most likely red. It's very distance-based. And because of that, we can get curved lines, a curved decision boundary. And you'll notice there's some false reds and there's some false blues in here. Actually, there's not a lot of false blues, but there are totally some false reds here, right? Well, they're actually red, but they're in the area of blue. Some of our other tools, like a support vector machine, is going to draw curved lines between things. Right, really, all of these are the result of a function trying to make the best classification. Right, this Gaussian process here is able to produce a decision boundary with a lot of nuance to it. And when we look at our trees, decision trees and random forests, these boundaries are all horizontal or vertical based on our measurements. Because literally, the comparison operators going on with decision trees are greater than or less than operators. So greater than or less than this first cut point here is classifying any X that's greater than that boundary. and Y that's less than that boundary ends up being blue. So yeah, we get some misclassifications in here, but with a decision tree or any tree, we have straight lines, which is really, really interesting. And the more straight lines we have, I'll give you a preview of decision tree. It's kind of like playing 20 questions. Y'all ever be on a road trip and play 20 questions? I'm thinking of something that's an animal, vegetable, or mineral. Somebody asks a question, then you try to ask successively more informative questions. It's what the decision tree is doing. Each question on a decision tree is another boundary. And so we're able to not just have a single decision rule, a very simple decision rule, but one with a bit more nuance here. Right. And some of these other tools with different shapes of distributions of the actual data. You'll see curved lines, you can see circular lines. The shape of the classifier doesn't really matter to us. What matters is the rate of misclassification or the rate of accurate classification. Andrew?
The number in the corner, is that representing how well that model is fitting the data? The corner of each picture.
Oh yeah, I see that, 0.95, 0.95, 0.93. Let's check the data itself. It's probably an annotation. So we've got some data, we make a figure, we iterate over the different data sets. Score, right here, score is the accuracy of a classification model. Accuracy is total true positives plus total true negatives over total observations. And I'd be willing to bet you that this score right here is being painted on the screen. Yeah. Probably not if not the score, then the prediction of the probability. Yeah, of that being the case. Yeah, Jen.
Just a question for clarification. So you just said that the shape doesn't necessarily
Hmm?
But isn't the shape piece, I mean, I know that this is just like to give us a visualization.
Mhm, mhm,
Doesn't the shape also represent the boundaries?
mhm.
So
It is, it
that's
does.
still, like,
Yeah, yeah, boundaries matter big time. Like that's how we're like able to classify things. We're not going to be charting these things out on our work. I'll put it that way. That's what I mean. I don't want you to worry about the shape because we're not going to quiz you on what does the shape of a Gaussian look like, right? Versus a decision tree. This is a visual to show us this is all about that decision rule, which is determining the boundary with the least amount of misclassifications. Yeah. So pretty wild stuff, right? Comparison of a whole bunch of different kind of classifier. And you can see even when the shapes are pretty different, we get some pretty good results. Maybe this 0.40 is pretty crummy. So this linear SVM is not the right tool to use on this specific data set. Some data sets will play nicer with some algorithms than other algorithms. It's not the algorithm that determines if it's any good, it's the distribution of the data itself. Yeah. So there's not like one perfect algorithm, right? Like in this last data set, even just visually, there's not so much overlap between the red and the blue. So all of these models are like 95 or better, right? The data set where we have more overlap, some of the models can get more convoluted. Like that nearest neighbors looks kind of, I don't know, like a sunflower. And the linear SVM, the linear part of the SVM means that these lines aren't going to curve around on each other, right? And some of these things might look like toruses, et cetera, or trees will look like a bunch of straight lines. So pretty cool stuff. And I'm going to give you a preview. Would you like a preview? Let's pretend that we've gotten our data, we've cleaned our data, and we've converted all of the categorical values into numbers. Can we pretend that for a moment? I'm going to show you the 2 lines where you can make a model. This is what I mean when I say sklearn is pretty simple. Regardless of whatever model you make, the first thing you do is you make the model. This is an empty model. It has yet to be trained. And we're setting the random state so that your results should match my results, right? The decision tree classifier is a bread and butter classifier, and this max depth argument is 3. So the max depth is the number of questions that you're asking your data. So 20 questions, the depth is 20, max depth. If you don't set the max depth, you'll ask an infinite amount of questions, which we don't want, because then you'll have each individual data point being its own class, right?
Questions like, so would it be how many options you have or no?
These are basically just like measurements, like with the back on the, where did that go? Oh, it's up here. Back on the overview here. What I mean by number of questions, we have 1 line here, 1 boundary, that's 1 question. And the question is, what's the color measurement? If the color measurement is greater than whatever this number is, then it's an orange.
So kind of would be like how many categories you, okay.
Not categories, because here there's only 2 categories, but we could have like 3 or 10 questions of this.
So,
Each-
oh, I see.
Each question gives you a piece of the boundary. Yeah, yeah. So here's another example visually. We have, this is a 3 class classification, classifying iris data. It's totally the hello world of ML, right? We have different species of irises, versicolor, virginica, and setosa. See how we have 2 decision boundaries here? This first decision boundary is if the length is less than 2.45 centimeters, then we know it's setosa. So the first question will always give, of a decision tree will always give you the most information. Because if we can classify all of setosa and the other categories are either versicolor or virginica, that's a really good boundary, right? That's a good decision rule. And if we have a second decision rule, then we'll draw the line, if it exists, between versicolor and virginica. So we can have many, many different questions. And if we were to visualize this as a tree in English, we would say, is the petal length less than 2.45? If it is, yeah, setosa. See how this is kind of geometric, right? Yeah, I think I saw Arsene. Yeah, go ahead.
You said that the first question is gonna give you the most information.
It'll give you the best, the most proper classifications that it can make. And then the second, with a decision tree, we'll do the lesson later. But the second decision will give you the second most information about how to classify things.
Okay, so like in this example, we can look at it and then kind of infer which question should be the first, depending on like the information that we get from here. But if we didn't have even if we didn't have this schema, this figure,
Yeah.
so how would we figure out what's the best question to ask first, or is that what we're gonna see later on?
No, you don't figure that out. The algorithm does.
No, now I got what you're trying to say. Okay, thanks.
Yeah, so I'll show you a little bit more of what I mean here. Step 1, you make an empty algorithm, an empty classification algorithm. Step 2, you fit your algorithm on your training data. You fit it on your X and your Y. Y is your target variable. Step 2. Step 3, we can visualize the tree if we want to have the tree explain itself. But really, step 3 is to use that algorithm to make predictions. There you go. 3-step process of doing a machine learning algorithm. We could have taught this to you on day 1 with perfectly clean data that was already prepared, that was already pre-processed, and it wouldn't make a lick of sense, right? But it's like 3 lines of code to get something useful, but it's a lot of prep work to get your data into a clean state, right? Ryan Miller is asking, sorry if I missed this, was the max depth parameter, how many groups to divide the data into? Yeah, you could, it's not the same thing as the number of possible categories, but yeah, Arsene has it, how many questions the algorithm is going to ask, at least with the decision tree. Because decision trees are like playing 20 questions, max depth is the highest amount of questions. If you draw one boundary, like we did over here, and it correctly classifies everything, you don't need to go any further, right? If everything is perfectly classified. Here's the cool part, V, you don't have to ask any questions in modeling. That's the model's job. Where you have to ask questions is, how do I get my data clean? And in the data exploration, exploring the relationships between variables, because you don't want to feed a column that doesn't inform the target. You don't give that to your model, right? But columns that do have a relationship, you run a chi-squared, they do have a relationship between column A and B and the target. Well, by gum, that's when you ask questions, because exploration is not automated in any way. Even if you had an automated script that charted out every possible chart, an automated script that automated every possible statistical test, you still need a human mind to interpret those results. So yeah, let yourself off the hook, Vasily. You don't have to worry about those questions. Your model's going to do that for you. We'll talk about our model internals as we get to them. We've only got a couple of minutes before lunch. So let's go through some of the pros and some of the cons. So logistic regression, we're going to definitely cover this one. It is a type of regression algorithm. Technically, it's a regression algorithm, but it's built to be a classifier. And with logistic regression, we can only use this on binary outcomes. So yes or no, churn, not churn. And we can get one of two outputs. We can get a 0 or a 1 from a logistic regression, or if we ask it nicely in code, it will give us a probability of the classification. So if it says 95% sure it's an orange, you can generally believe that. The nice parts about a logistic regression, it's quite interpretable, and it's good for understanding the influence of multiple different features on a single outcome. Pretty flexible, so we can either choose our output to be 0 or 1, or a probability between them. Logistic regression is very easy to implement, right? It's very efficient also. It doesn't require a lot of computational resources. Here's some of the drags, here's some of the cons. We do need to remove attributes which are either uncorrelated to the output, there's not a relationship to the output, or we should remove variables, independent variables that are tied to each other, tightly correlated there. And logistic regression, while it's really fast and pretty darn easy, it's not always your most accurate compared to some other tools. Yeah, Arsene.
So when you're talking about trimming, is that where we try to identify outliers?
Where you try to handle outliers? No. Outliers can have an influence on your model's results. We'll talk about that later throughout the course, but really, you make a model, you fit the model, and then you use the model to make predictions. That's like it. And then you evaluate those predictions. I don't know if trying to oversimplify this is helping or hurting, but yeah, we do need to consider outliers, but you can totally make a model that contains outliers, especially if the data you're going to be making predictions on also has outliers that extreme. Did that speak to your question, Arsene? Or leave you with another one?
Yes, thank you. You know, I think it's just the 3 steps, and then no need to figure out the outliers.
Yeah, that is an arguable comment.
Like not necessarily.
They're either a big deal or they don't matter, and it depends. It's the data science answer to everything.
Yeah.
For right now, don't worry about it. Yeah.
I think maybe our set, if you can correct me if I'm wrong, was pointing out like the cons and order logistic progression in terms of the attributes. We also.
Oh, yeah.
Is that saying then that there is algorithms that we can use that we don't have to worry about those attributes? Because they kind of worry with them. Does that make sense?
There are other algorithms that are less sensitive to that. So let's say if we have X and Y and we're trying to predict Z, right? If X and Y are tightly correlated with each other, then how do we know which one is predicting Z? That problem is called multi-collinearity. It's a very fun word to say, but it's more sensitive to that.
And that would be kind of, in a sense, like if we brought it down to like, let's say, we're taking out the columns that just don't make any sense to have there, and just focusing on, let's say, columns that actually make sense.
Correct. And maybe X and Y are so correlated that we could turn them into another new column. Like if you have length and height, maybe the new column is area. And area does a better job than either one of those individually. That's a very simple example,
Yeah.
but based on domain knowledge the domain knowledge of X times Y giving you area, right? But based on the business's needs or something specific, yeah. Cool. All right, we're gonna break for lunch, folks. We'll come back and we'll talk about some of the pros and cons of decision trees, forests, KNN, and then we're gonna get our hands on some data. So let's do it. Have a great lunch. We'll see you.